Can you guys hear me? Yeah, this Zoom link didn't work properly. So I'm hoping everybody can get in. Let's just give people a minute to join. Alrighty, are there questions before we get started? Last time we did the Heine-Borel theorem, and it's difficult, and there were lots of questions afterwards, and there were also lots of questions about it during the office hours. So I'm going to spend some time trying to go through it again. Let me just show you the updated Canvas site, and I put a few documents up there. So let me share the screen and see. Right, so you should be able to see my screen now. And I put a few documents up here. So Heine-Borel, this is a teaching note going over what we did last time, and also what I'm going to start doing here one more time. Because compactness is so important, I put up a document here that'll give you an overview of like a history of compactness, how it was developed, and how it brought together researchers from a different area of math. And then the last document I put up here is a set of sample problems for the upcoming midterm, and put up solutions to some of them. We'll talk about some of them in class when we get closer, but for those of you that want to start working on them, you're more than welcome to. Okay, so right now what I'm going to do is I'm going to go over the main step of what we did last time one more time, and you can find more information in this Heine-Borel file here that's up on Canvas. Right, so when you see something now that doesn't make sense to you, it's like this compactness concept. This is quite important. This is if you just Google compactness, and you will find lots and lots of references. This is one of the most important concepts that you are going to see in this class. So spending time and understanding, spending time to understand this properly, I really think this is worthwhile. So, so let me start by going through this argument from last time one more time. Let me try to see if we can get it to work. Right. So the starting point is that we want to show that an interval, say alpha to beta, is compact. This is the prototype sets that are compact. So how would one go about doing this? So what does it mean to be compact? Well, it means that you can take any open cover. So this is a collection. We call them O, lambda. This is any collection of open sets. Of open sets. Any cover, right? So O lambda of open sets can be thinned to a finite open cover. Right? So what does it mean to be an open cover? That's this aspect here. Right? What does that mean? Well, it means that this interval is covered by these open sets. Right? So the inside is a big union. And what does it mean that it can be thinned to a finite open cover? Well, this means that if I throw away all these sets except for finitely many, I'm still going to be in there. Right? So there'll be some O, there'll be some lambda, union over lambda 1 up to lambda m of these O lambda. So there are finitely many here. This is m is something in the natural numbers. Whereas this guy over here, this can be really general. This can be anything. This lambda here can be anything. This one over here, you select out finitely many of this huge collection over here. So this one here has a much more, potentially a very complicated structure. So for example, so some examples could be, you would have that this one here is a natural numbers, right? That's infinitely many. So you would have that O lambda or O, like O lambda here could be one of the ones we looked at a bunch of times. It'd be like -1 to, I don't know, 1 over n. Like these are open sets, and they cover, if I looked at the union, of these guys, I'll have -1 to 1, yes? Right, so you will cover lots of things. But you could have a much more complicated structure. You could also have that lambda could be, it could be R. You could have lambda here could be something crazy, right? It could be R to the R, like the space of functions that go from R to R. Like there's no limit to how complicated this object here is. Whereas over here, you just have finitely many. So it's a harsh condition, right? I want to say that a set is compact if you can take any open cover, all and every single one of them, no matter how complicated the structure here is, and you can thin them out such that the thinned out collection is finite. I'm going to take the union, you're going to cover the set, in this case, the closed interval. Are we all good so far? Yep, so far so good. Okay, so then how do we prove that we can do that for this particular set? Well, so the way that I've proposed to do it in the lecture last time, and also the way that this note does it, is that it introduces this set B. And the set B are those x's living between, say, alpha to beta. It doesn't you could have a richer structure here. It doesn't have to be just alpha to beta. You could also have alpha to beta. You could have some, it doesn't have to be necessarily beta that you have here, but beta works. And then what you want to have is that when I look at it from alpha out to x, that this closed interval here, like this one can be covered by finitely many O lambdas. We're not saying which ones, we're just saying that there exists a finite collection of these open sets. So when I take the union of these open sets, I get something that includes the interval from alpha to x. And what we did last time was we were playing with the supremum. So we want to show that B is not empty, and B is upper bounded. So this is not terribly hard, because why is it not empty? Well, if I just pick the left endpoint, I want to show that the left endpoint is in here at least. The left endpoint is in here, so I want to show that I can choose some x such that this is true. Right? This is not. I want to show it is not the empty set, so I need to give me some element that is inside the set B here. Okay, so pick the left endpoint, right? Alpha obviously is in that interval, so it can be covered. Right? It belongs to some of these open sets because the union of all of them include the closed interval, so it will include alpha. And then I can put a little ball around it because this is open, right? So this here implies that there exists some little ball, an epsilon. I put an epsilon around it, so minus epsilon plus alpha, plus epsilon plus alpha. I put a little ball around my alpha, right? And then I'm going to be still inside this O lambda. So if I look at the interval that goes from alpha to say alpha plus say epsilon over 2, but this here is inside that interval I have up here. Right? This is inside alpha minus epsilon, alpha plus epsilon, right? And this is inside O lambda. And this is a single set. Right? So this can be covered by a finite union of these open sets. Indeed, it's just a single one. So B is not empty because it contains alpha. When B is upper bounded, and that's because it's considered to be a subset of points x's. We're considering this thing here is a subset of alpha to beta. Right, so B is upper bounded. It's upper bounded by beta. So what all this stuff here shows is that the supremum of B, this is a number, and this is some element inside alpha. We can even make it more precise if we want. We know that it's going to be between alpha plus epsilon over 2 and then up to beta. Are we good so far? Otherwise, you're welcome to interrupt and ask questions. So the supremum, I have a non-empty set, it's upper bounded. The supremum is going to be in here somewhere. So we're going to prove two things now. So the first thing we're going to prove, so the first one we're going to prove is that if I looked at the interval from alpha up to the supremum of B. And this can be covered by finitely many of these O lambdas. Right, so that's the first thing that we're going to prove. And then the second step we're going to prove is that this supremum here, this is actually equal to 1. And when I talk combining these two, right, then I'll be able to say that alpha up to 1, or beta, I should say. Beta is the upper bound. Beta is the upper bound. I'll prove that. So that means that the interval, the closed interval from alpha to beta, this can be covered by finitely many O lambdas, and then we're done, because this was the claim. So in the lecture last Wednesday, I tried to combine these two into 2 steps, and I think that caused confusion. So let me not do it this time. We try to separate them out, break it down into a few more steps. So why can this be covered by finitely many O lambdas? Well, so if you work out the steps, if I stay a little bit to the left, I will know that alpha, and then if I subtract a little bit from the sub B, if I subtract away just a smidgen, if I subtract away a little delta, so for all delta positive, this thing here, this can be covered by finitely many O lambdas, right? Because if I stay a little bit to the left of the supremum, right, the supremum over B, well, this is the, if I stay a little bit to the left of this X here, if I choose X to be just a little bit smaller than the supremum, well, then I can be covered by finitely many of these O lambdas. Otherwise, you would not have the supremum. So we have this, and then the question is, if I just need to cover this last guy here by something. But we use that the supremum was given to be here. Right? And this is, of course, this is going to be inside that big union. This is going to be inside that big union. So the supremum is inside that big union. That means that the supremum is somewhere. Right? So the supremum, there is some lambda. I think we called it lambda 1. They exist in lambda 1 such that this supremum is in that set, because the supremum is inside the union, so it has to be somewhere. But if that's true, I can play the same game as I did before. I can find, if I look at the open interval, I'll take the supremum of B, I'll subtract a little bit. There exists some small ball around this point that'll be inside here, because this set here is open. So I'll take there's some small epsilon such that this thing here is going to be inside, that open interval is going to be inside that open set here. This is because, O lambda is open. This one here, and this is because that supremum was inside that union. Okay, so Priya has a question. Let's see what Priya says. What implies that the supremum? So that's this one here, right? This is because, let me write that right here. This is because you know that the supremum, what we argued over here, right? You know that the supremum takes its values into alpha to beta, right? And this thing is inside that union. Right, so I have an element inside a union. if I have an element inside a union, it has to be in one of the elements that I'm taking the union of. Does that make sense? So there's this has, so that gives you this one, and then you use that this part, well, we have a collection of open sets, right? So we have a collection of open sets. I have a point in an open set. I can put a little interval, a little ball around that point and stay inside it. But now we're in shape, right? Because I play the same game as before. But if I looked at the interval, if I looked at the interval, say sup B, and then what do? I'll go back to minus epsilon over 2, and then go up to sup B plus epsilon over 2. This thing is going to be smaller. This is going to be inside this interval here, right? So that's going to be inside O lambda. But I know as soon as I go just a little bit to the left of the supremum, I can be covered by finitely many. Right? So I can write now the interval from 0, not 0, alpha, keep writing 0 here, from alpha to the supremum of B, right? I can write this here as alpha to the supremum of B minus epsilon over 2, union supremum over B minus epsilon over 2 to the supremum over B, and then to the epsilon over 2. Right, and this one here, by what I have up, this can be covered by finitely many. This is covered by finitely many. Well, and I know this part here, but this part here, this is a subset of O lambda 1. So then I have finitely many union 1. And this means that all this stuff here, this is covered by those plus this one. This is covered by finitely many. In the O lambdas. Does that make sense to you guys? This was the first one. Now we could. So now we know that this is true. So the next part is to prove that the supremum is actually this upper bound. It's actually the right end of the interval. And how would one go about proving that? 2. Well, there are many ways to argue, but we could say, what if the supremum would be less than beta? Right. If we had something like that, could we create a contradiction? What if this happens? We know that it's the upper bound is beta, but what happens if we are strictly below it? But I mean that, okay, so Priya has a question, but that's what it means to be compact. I mean, that is, a set is compact if any open cover can be thinned to a finite cover. That's the definition of compactness. This is, there's no, we are trying to show that A to B is compact. That's right. So the starting point is to take an open cover of A to B and show that we can thin it. right? So for this thing to be compact, any open cover of open sets can be thinned to a finite cover. So we have this we need to show this. We need to show that any given open cover of this interval can be thinned. So take an open cover and show that it can be thinned out. Right. So if the definition of compactness is that A is compact if any open cover can be thinned to a finite open cover. Right. So to show that A being an interval is compact, we let O lambda be an arbitrary open cover. Then we must show. Then we need to show that we can thin it. Can you follow me, Priya? Okay, so that's how the proof goes. We've in the proof these O lambdas for a completely arbitrary set. We're not specifying what this here is. This is because it has to be arbitrary. It can be any one of these. We don't know. We're trying to thin it out and show that, well, that we're successful. This can actually be done. And how would one go about doing it? Well, there's a two-step process being proposed. There's a two-step process. There's this setup here that's being proposed, and then we're studying the supremum of it. And if I can verify these two steps here, I'm done, because then I'll just take the beta and put it in here, and then it says that the interval from alpha to beta, this can be thinned, and this can be covered by finitely many. And so then we'll be done. Then we'll have compactness. We did step one, so now we're attempting to go about step two here. What about if this happens? What about if this happens? Well, we play the same game, right? Sup is still going to be the supremum. This is still going to be an element inside that big union. This is still going to be in there, right? It's a number. In this case, now strictly we're assuming that it's strictly less than, but it's still going to be in here. So we can write this. We can write this here as something inside, and there's going to be some open set that will contain this point. And then play the same game, maybe put a little open interval around it. So now we're going to use, because O lambda is open, we can put a little epsilon around the point and then stay inside it. Right? So there exists one of these things, so that when I look at the open interval from sup and then go a little bit back to epsilon and then a little bit up, I'm going to be inside that open interval, is going to be inside that open set. And then what? Well, now we come to the time where we use this property here, right? We choose, so maybe choose an n. So so that the supremum over b plus this is delta over, no, there's epsilon here. Take that epsilon over n such that this is less than 1. I can do this. This is okay because we had the assumption that the sup over b was less than beta. Right? Had it been equal to, then I couldn't do it, right? If this one had been equal to that one, I could not do this. But I take this epsilon that I'm given and I just scale it by n. I choose a big enough n, then this number here is going to be so small that I can squeeze it in between here. And now we're going to get a contradiction, because when that happens, I can move beyond this sup b. And the way that I'm going to do it is very similar to before. We're going to be looking at the interval from 0 to sup b plus this epsilon over n. Let me just choose multiply it onto a half here as well. That's still fine. I just want to make sure I'm inside. I just put a 2 here. That's fine. I can write this here in terms of, well, I'll do the interval from 0 to sup b. I can even do sup b minus a little bit if you want to be sure. Sup b minus, say, epsilon over 2n. And then I'll take union. And then the last piece would be from sup b minus epsilon over 2n to sup b plus epsilon divided by 2n. Again, as before, this first part here, this can be covered by finitely many O lambdas. And this one over here, that interval we have here, this is going to be inside, this is going to be inside this one, so that's going to be inside O lambda. This one here is a subset of O lambda. So there we have finitely many again. We have this O lambda. So that means that this interval here, this can also be covered by finitely many. Put these two together, then that's going to imply that the interval from 0 to sup b plus this epsilon over 2n, this can be covered by finitely many. But that's a contradiction, because sup b, this was the biggest, this was the biggest number, and here we found one that's even bigger. So this is a contradiction. Because I was able to go a little bit further than sup b. And that means that this thing here fails. Okay, so that means that we know that it's always less than or equal to. So the only thing that remains is that sup b has to be equal to beta. How does that look, guys? Is this better than the other day, or is it still confusing? Are there any questions on the things that we did here? One thing that came up in the office hours yesterday was that I was creating, I was been creating these problems for your midterm and also for the the sample problem. So maybe here was something I was thinking about putting on your midterm. So here could be a question. Like you could say, where does this stuff go wrong? Where does it go wrong if I didn't have a closed set? Like what about what about if I took 0 to 1, right? And this would be inside some open set like the union. So now we're running over the natural numbers of say -1 to say 1 minus 1 over n. So this here would be our ON. So I should not be able to do this stuff here. So where does it go wrong, right? So you could say, so what is, if I looked at the same set, if I looked at B tilde, so I would have, this would be my x's, such that 0 to x, and then we keep it open here. But this B tilde here, that this would be, this can be covered, say by finitely many ONs. Then I could ask, so what about here? Like what is B tilde equal to? Can I write this here as an interval? What is the supremum of B tilde? Is the what is this equal to? And one could also ask, what is B tilde? This is an interval, right? That was a conjecture one of you guys made yesterday in the office hours, is that is B tilde an interval? And if so, which one? Was to take a specific open cover of this specific open set and try to redo the proof, like something is going to be off here. Something is going to be off that you're not going to be able to have, you're not going to be able to put, I mean, we know that we cannot cover this interval here just by finitely many, right? O1 is not a subset of just finitely many. So if you take nk, take k equal 1 to say m of O nk, but that is not possible. You can't do that. So something here is going to go off. So something is not going to work the way that it did in the proof. And now try to identify exactly what it is that won't work. But that might be one way to try to internalize the proof instead of just seeing me go through it. Any questions or comments before we move on to something else? But this here is the most difficult part of the Heine-Borel theorem. So I want to look at some of the other components that went into this theorem. So let me write down the theorem again and just fill in some more of the missing pieces. So the theorem that we're working on. The theorem that we're working on is this Heine-Borel. So K is a set here in R, and we have that K is compact, if and only if K is closed and bounded. If and only if all open covers can be thinned to finitely many. Right, so what we've been proving here is that we had a prototype, and last time I also showed you that what we did in the proof, right, we did 2 implies 3. 2 implies 3, right? What we did was we took K, we put him inside some big box, alpha to beta, right? And then we know now we can thin this, and then we can use that to also thin out a cover of K. That was what we did. The other parts, how would you go about? So we have do 1 to 2. So in Abbott's notion of compactness, he says that any sequence has a convergent subsequence within the set K. And so how does that prove that we have? How does that prove that we have a closed and boundedness? Well, one way to go about doing that is to say that, so assume, so we have 1, right? So assume K is not bounded. Maybe I should write out here that this is in Abbott's world. Abbott's definition is that any sequence inside K has a convergent subsequence that converges, has a convergent subsequence that converges inside K. It is this sequentially compactness of property. Right, so if you assume that K is not bounded, then what? If K is not bounded, then we want to get a contradiction with the statement up here. Right? So if K is not bounded, what does it mean that you're not bounded? Well, you take any big number. I can find something. Inside here, so we call that xn, such that xn is big. If it's not bounded, then you give me any number you want. I can find a point inside the set that is not bounded, such that you get something that is even bigger. But with that property, then how would so that's my sequence, and now the statement is that I can find a convergent subsequence. Okay, so let's take a convergent subsequence xnk inside that sequence that satisfies that property. Then look at how big is xnk. Well, it's going to be bigger than nk. And then use that it's a subsequence. This is going to be bigger than k. And so that means that x and k, well, it converges to plus infinity, and this is not an element, right? K is a set inside R. This is not an element in R. So this is a contradiction. You got to have boundedness. Right, so this is a contradiction. And the same thing, if you're not bounded, you can play a similar game. I'll just show you how to do that. Sorry, this is a bounded. If it's not closed, you can play a similar game. If we assume K is not closed, and play a similar game. Yeah. Maybe not. Let's see. I take to see that K is closed. What do? We take what do? We take a sequence. So let's try to take a sequence that's inside K, and show that be convergent, and then show that that the limit is actually inside K. Take a sequence that's convergent, and now the question is the limit there, right? And if it is, then we're going to get closedness. And we use the definition of compactness. It says that so use this Abbott's definition of compactness. Now I have a sequence, so it has a convergent subsequence. So use compactness to extract x and k. This is a subsequence of this xn up here. And then we know that the subsequence converges. So x and k, I'm going to take the limit. This element here is going to be inside K. Right, but the original sequence is already convergent. So when the original sequence is convergent, then any subsequence is going to converge to the same limit. So this here is going to be equal to the limit of xn as n goes to infinity. And so there you have it. The convergent sequence inside K. This is going to be inside. The limiting point is going to be inside K as well. And you can see here that this resembles. Maybe just have a little example. Put it in red so you don't confuse it with a proof. But if I were to consider like this interval here, then I could take a convergent sequence. I could consider xn to be 1 over n. This is convergent. So therefore, any subsequence of this thing is going to converge to the same point, namely 0. But so any subsequence x and k being inside this 1 over n, it converges outside K, outside this open interval. It converges to 0. So this interval here does not have the property that we used up here. And that's because this interval here is not compact. It has this openness over here, and this is what we're exploring. What this argument here showed is that if you have a compact set, in the sense that sequences, you always have convergent subsequences inside the set, then you're going to get a closed and bounded set. And then what we proved, what we had proved was that all open covers can be thin. So we have now proven 1 to 2 and 3 to 2. We have proved before we took a closed bounded intervals, we've proven K is compact in this sense. That implied number 2. Okay, and then we proved 2 implies 3. So the only thing that remains is looping back around up to 3 implies 1. I didn't prove that one. I proved it. I broke it up. I followed the textbook, so we'll follow the textbook now too. Let me keep track of what we have done up to this point. So we did 2 to 3, and then we did 1 to 2. The next one that I had was 2 to 1. 2 to 1. So I want to take a close bounded set and prove that it is also compact in the sense that any convergent any sequence has a convergent subsequence within the set. So if I can do that one. We're doing 2 to 1, so I want to say that I take a sequence. Take a sequence inside K. Okay, and then I want to prove that there exists some set X, there exists some subsequence inside it that converges inside K. How would I go about doing that? Well, all I have going for me is that I know that the set is closed and bounded. Oh, Priya has a question. Why does the limit of a subsequence equal the limit of a sequence? Well, in general, no. So the property is that if AN converges to A, say in R, then any subsequence, then any ANK also converges to the same limit. Is that your question? Priya, is that your question? No, read what I have here. Is this your question? No, that's not it. Okay. It's the part of the proof from 2 to 3. Is it this one here? But that's what we have, right? You have a convergent sequence, and I want to show that the limiting point is inside K. So, but I have a convergent sequence. Then I'm going to take a subsequence, and I know that subsequence, because of compactness, I know that subsequence is going to converge inside K. Right. So this one here is given by compactness, and this part here is given because xn converges. So if xn converges, then any subsequence is going to converge to the same limit. Okay. It's the other way around, like so it's if AN doesn't converge, if it doesn't converge, AN K, which is inside AN, can still converge. Right. You can have that the original sequence is like bouncing around and oscillating, and then you can find convergent subsequences. Like in that case, I mean, these subsequences, they could all have different limits, and they wouldn't necessarily be the same. But if the original sequence goes somewhere, then every subsequence is going to go to the same point. Okay. Let's see if I can come back to. See if I can come back to this one here. Right. So now we are assuming 2. Let's just bring out what 2 was one more time. There's 2. So bringing up 2 here. 2, K is closed and bounded. Okay, so take a sequence, prove that I can find something that converges inside K. But this is not bad because we have a big gun available. We have the Bolzano-Weierstrass. The Bolzano-Weierstrass says that boundedness, boundedness, right? K is bounded. Boundedness of K gives a convergent sequence. So then how do we get it to be inside K? And then we use closedness. Closedness of K. Closedness of K. This is going to imply that X and K converges inside K. So that's not bad. Everything is hidden in this Bolzano-Weierstrass theorem that says that when you have something, you have a bounded set, you can extract. You have an infinite number of points. You can extract. If you have a bounded set in R, then you can extract a convergent sequence from it. So here we have bounded set, extract something that converges. Then you also, the requirement in Abel's definition is that that thing that's going to converge is not enough. It has to converge inside K. Okay, so we have to have its limit points. We have to make sure that the limit points, that the limit of the sequence is an element of the set, but that's going to be true because of the assumption that the original set was closed. So this gave us, you can see these implications here, they're not nearly as bad as the one we've been working on. So this gave us this one. And then we're almost there. Then we should just have, what is it going to be? 3 to 2. If I do 3 to 2. I do 3 to 2. Actually, 3 to 2. All these open covers, they can be thinned to show that this gives us a closed and bounded set. Okay, let me try to do that. Okay, so consider the open cover OX. And this is going to be nothing else than V1 of X. So remember what these were. These were these open intervals of radius 1. And now the X here, the index here, this is we index by K. So you can see we are really taking advantage of the flexibility. We're not just using. This was what I was trying to say over here. This index set can be fairly general, right? It can be natural numbers, it can be real numbers, it can be functions. And here we're moving over like this, the index that we're using is K. And of course, by having this property, we will have that K is a subset. K is a subset of this open cover. Because any point on the left-hand side will be embedded in one of these open intervals of radius 1. And then the assumption is that we can thin, K satisfies that we can thin this, so thin it, thin this OX to just a finite number. So thin it down to write this, let's write it as O, maybe X1, so OX M. So you can thin it down. You can thin it to this. What does it mean to thin it down? It means that K, you don't need all these sets to cover. You can just cover from a little m equal to 1 to capital M, some finite number of these open sets. Right, and this here is bounded. This one here is bounded. Because each of these ones are bounded, and I take a union of finitely many bounded set, I'm going to be bounded. So this shows boundedness. We call this the A. We also need to show that it's closed. So this is a bit more involved. Let's see if I can get it to work. We also need to check. So this shows boundedness. We also need to show to see that K is closed. We argue about contradiction. We argue about contradiction. Okay, so if it's not closed, then there's a limit point of it that won't be included in there. So we argue by contradiction. There exists some point, so the X0, right? K is inside R, so this point here is outside K. This is a limit point. The existing point, which is a limit point. Okay. We're going to see if we can find. We're going to see if we can find a contradiction out of all of this. The way we're going to go about it is we have to create open sets. And so what we do is this time we go about it, we're going to index them by n. So we're going to look at these open sets. You're going to take the point in question and make it open, -1 over n, 0 plus 1 over n. This is closed, so I take the complement. This is going to be open. And if I take the union of all these, what will I get? This n here is now running in the natural number. So we don't have, before we use the index, K was a subset of the positive real line. So that was uncountable. And now we're back into a countable setting, if nothing else. But if I take the union, what would I get? So to take the union of all these open sets, it's not hard to see. Like you're looking at the complement as n increases, the intervals here, you get smaller and smaller and smaller. The complement is going to get bigger and bigger and bigger. I'm going to get here that this is R less my X0, and inside here is where you'll find K, because the assumption was that X0, right, was not there. this implication here. This is because what we had up here, that x0 belongs to R less than K. And K is, of course, a subset of R. So we have an open cover. We can thin it. So thin ON to say ONM. So we want to have the same property. So K is inside. Now we don't do the big union, we just do the little one. Of these O and M's. And what are they going to be? Well, we use the formula. We have a formula for this thing. This is equal to R less than, and now what? So we'll have x0 minus, and then what? 1 over, we're going to get a maximum down here of these n1 up to nm. We've had that in class at some point too. And then you have x plus the same thing. And this is too much to write, so I'll start calling this here. I'll call this thing here for n0, and it's the same one as what you have over here. So what we see here is K is inside this object's complement. So if I take the intersection with this set, it won't work. It's going to be empty. Here I have x0 minus 1 over n0, comma x0 plus 1 over n0. This is going to be empty. But that is not good because what? Inside this open interval, I'll find the open interval V of 1 over n0 centered at x0. So I take the intersection with the big set, I'm empty. So of course, when I'm going to take the intersection with the smaller set, I'm going to get that K intersection with this guy. This is not going to be, this is going to be empty. But then there's no way, so x0 cannot be a limit point. So those were all the implication in the theorem. And you can see this part here is used two different index sets for the open sets. It was K, and then the other one was the natural numbers. But one can use a lot more general index sets. So we have a little bit of time left. So let me just, are there any questions on the proof? Or I wander off on some tangent. These index sets, one thing that comes up in Riemann integration. So when you talk about lambda in lambda, this index here, this can be very general. We often used to saying that, well, if I can take, so often we use, and one thing we then do is we're going to say stuff like, if I have lambda and say beta inside n, we can compare. We can compare, like lambda is less than or equal to beta, or beta is less than or equal to lambda. We can also do this when we move into, say, an interval. If it was 0 to 1, same thing holds. So for Riemann integrals, when you're looking at an integral from, say, 0 to 1 of f of x dx, this is just to give you an idea about that this set here can be something that is very different than numbers. So for the Riemann integral, the following lambda comes up. Okay, so, and we're going to be doing Riemann integrals in a few weeks. So we're going to be doing Riemann integration at some point in the upcoming weeks. This set here comes up, and so what is it? So lambda, this is going to be the set. This is the set of finite partitions of that interval you're integrating over. So say 0, 1. Right, so for example, you could have 0, a half, and 1. This is an element in lambda. You could have that a third and a half, and I don't know, 1 divided by pi. This is an element in lambda. You could have, it doesn't have to be just 3, right? It could be a lot more. You could have a seventh and a ninth. These are all finite partitions of the interval. Typically you order them, so the smallest one comes first, but not even that is necessary here. So this thing here comes up when you want to do Riemann integrals, because the way that you're going to do this integral is going to be to divide. You're going to be dividing the x-axis into a finite partition. So you want to have a partition here, and it's going to be a finite partition. And so we have your function. What you want to do is you want to put squares underneath it somehow. And then you want to add up these rectangular shapes. So you need a partition down here. And so that could be your lambda, and it will be for this Riemann integral. And so again, we're looking up here, we want to be able to compare. So how do we compare? How do I compare two elements? Right, so lambda, this could be, say, the first one, 0, a half, and 1. And my second one, my beta, this could be, I don't know, 3/4 and 5/6. How do I compare lambda being bigger than or smaller than beta? So because the set here is so general, you can't do that. Like this stuff here and this stuff here, this makes no sense. So instead, what we're going to end up doing is we're going to talk about orders. So what we're going to be having is, so we cannot compare lambda and beta like that. But what if I change beta here to be something else? What about if I would compare lambda beta and then say gamma? What would happen if I would put inside gamma 0, 1, 3/4, 5/6, and 1? What would we then say? Would we say that, then we would say that lambda is smaller than gamma, because lambda is a subset of gamma, we will say that beta is less than gamma because beta is a subset of gamma. So while it's not possible to compare all these partitions, what you can do is you can take the union, and then you can say that the union is going to be bigger than each individual one, simply because you have this inclusion property. Any questions about this part here? I want you guys to move away. I would like you guys to move away from thinking about lambda here just as being something that has this structure. In general, when you talk about an index, this can be really this can be a huge mess. And here we're not even assuming that we can compare indices. This may or may not be possible. The only thing we are saying is that give me any collection of this arbitrary set. If you compact, I can extract a finite number of them. Right? And so if it's these finite partitions that we need for the Riemann integral, I'll be able to extract a finite number of these partitions, a finite number of finite positions, if it is that the set has this compactness property. Any questions? We are running out of time. Any questions? No, it's not. It's not. This is not a power set. I mean, this here is not a power set. I'm not able to, inside here in this case, if I would take 2 to the interval 0 to 1, then I could take a set A in here. This could, for example, be A is equal to right. Pick the Cantor set. The Cantor set is not this does not belong to the set of finite partitions. And finite partitions is a string of numbers. So should we say that x1 up to xn, these numbers inside 0 to 1 is a finite position? So take a bunch of numbers, so just between 0 and 1, and they're all different, right? So I is not xj. And you can, even if you want, you could order them. You could also say that xi is less than xj. So x1 is less than x. Yeah, we could write that out. There's no harm in doing that. And n here is a natural number. Yeah, so this here could also be an index. This we could also have chosen this set here as being lambda, but in this particular application, this is not. This is much smaller than the power set. And you can see how it really works well with integration, right? If I want to think about, I take a partition So you take a lambda inside this partition. How would I think about an integral? How would I think about an integral over lambda? Well, how would I do it? I could take left endpoints approximation. So I could have f of, say, x1 times, and then it will be what, x2, so xi plus 1 minus xi, right? And then I'll have an integral over I from 1 to, say, n minus 1. And this is how I would integrate. And then you could have this property over here by inclusion. So you could, if I would have a finer partition, so beta is not finer than lambda, right? But gamma is, because I have more points inside here. So I'm going to get that there's going to be some structure, and you can see how these partitions play well with integration. Simply because I put out the partition down here and just compute the area of these rectangles. And I would not be able to, if I wouldn't know how to do that if I would take an arbitrary subset of the interval 0 to 1 and then perform integration like this. I wouldn't be able to write this as a sum. I wouldn't know if I would pick lambda here, and lambda would be an arbitrary set inside here. I wouldn't know what this should be had you taken an arbitrary subset of the interval 0 to 1. I wouldn't know how to define this integral for such a subset, but I know how to do it for these finite partitions. So this structure here is too rich; it's too complicated for this application. Are there other questions? Any other questions? Otherwise, it's time to call it quits. And I'll see you guys in person on Wednesday. All right, take care.